All right, this recording is of 5-3 part 1 notes. The students in the room have been advised that if they speak, they'll be in the video. And this is 2014's fifth period. Yeah.
Go Lakers.
All right. Today we're going to focus on conditional probability, independence tree diagrams, and the general multiplication rule. Here are our learning objectives. Let's start with conditional probability. The probability that event B will occur given that event A has occurred is called conditional probability of B given A. And here's how we notate it. This little line right here is pronounced given. So this is the probability of event B given event A has occurred. And here's our first problem. Is there a volunteer to read that?
I'll read it.
All right, go for it.
Students at the University of New Harmony received 10,000 course grades last semester. The two-way table on the right breaks down these grades by which school of the university taught the course. The schools are liberal arts, engineering and physical sciences, and health and human services. College grades tend to be lower in engineering and the physical sciences, EPS, than in liberal arts and social sciences, which includes health and human services. Consider the two events. E, the grade comes from an EPS course, and L, the grade is lower than a B.
Cool. So we have a two-way table, and we last were working with these in chapter 1. And it starts off with saying, find the probability of L. So event L was the grade is lower than a B. So looking at this table, grade lower than a B. That would be this column right here, right? Mm-hmm. Okay, so we need the sum of all of these individuals over the total number of individuals. So let's see, 2268 plus 800 plus 588, all over, how many people are we talking about? How many grades are we talking about? 10,000. So that is approximately 0.3656. The next part it says is interpret this probability in context. So what does that number actually mean? One way of interpreting this would just be to say 36.56% of all grades were below B. Let me zoom out. 36.56% of all grades were below B. Now, in this particular interpretation, we don't have anything about in the long run or over time. This is actually just a fact here. For these 10,000 grades, 36.56% of them were below a B. Now, this next one's interesting. Find the probability of E given L and the probability of L given E. So let's see. The probability of E given L. In plain English, that means find the probability a student is an engineering student given they got a grade below a B. So what we need to look at for this one is all the people, or all the grades that are below a B, and figure out what proportion of those were engineering students. So it looks like 800 over all of this, the sum of this column here. So this is 800 over 3656. And that is approximately equal to oh, sorry, I missed a decimal here. 0.219. Does anyone want to try to interpret that number? Want to try it? Go for it.
21.9% of all students who got a below a B were engineering or physical science students?
Perfect, yeah, that's it. And in contrast, probability of L given E, this would mean of the engineering students, what proportion got a grade below a B. So on this one, we're not looking at this column anymore. We're looking at this row. So this should remind you of conditional distributions from chapter 1. You remember when we would like cover or cover?
Yeah.
That's what we're doing again here with probability. So let's see. This one's going to be 800 over the sum of that. There was 1,600 engineering students. So this equals 0.5. Now the next question says, which of these conditional probabilities tells us whether this college's engineering and physical science students tend to earn lower grades than students in liberal arts and social studies? Really, neither of these tell us that. This one's a start. This tells us what proportion of engineering students got low grades. What we could do is find the probability or the proportion of liberal arts students who got low grades and the proportion of health and human service students who got low grades and compare them to this one here. So we would really need 3 conditional probabilities to answer that question fully. Do you want me to write something or just that was adequate?
That was fine.
All right, cool. Independent events. These have both a formula definition and a common sense definition. 2 events such that the occurrence of one has no effect on the occurrence of the other are called independent events. So that is, the probability of A given that B has occurred is just the probability of A. See, that given B gives us no additional information about whether the event will occur. So another way of saying that is the probability of B given A is just the probability of B. And dependent events are events that are not independent. So this would not hold true. So for the next 3 examples here, we're going to decide if the events are independent. So example A. Shuffle a standard deck of cards and turn over the top card. Put it back in the deck and then shuffle again. And turn over the top card. Define events A as the first card is a heart and event B as the second card is a heart. So is event A and event B independent here?
No. Yes.
Who says,
Oh, no.
who says yes? Who says no? All right. The answer is yes, but I'm interested in why no.
Oh, because if you don't put it back in, then there's one heart that's not accounted for.
Yes. And in this example, you are putting it back in.
Oh. Oh.
Yeah. So you agree with us. Yeah. If
Okay.
you don't put that card back in, it actually it matters. Yeah.
Oh, okay.
So let's write independent. Since we are putting the first card back, and then reshuffling, that's important as well. We're reshuffling the cards before we draw the second card. Knowing the first card will not tell us anything about the second card. Let me ask you this. If I were to ask one of you for a penny, and say I grab that penny, and that penny's from 1993. The date on that penny is 1993. And I put it in my pocket. So let's think event A is the first penny I select at random is from the 90s. So I grab a penny, and then I put it in my pocket. And event B is the second penny I select is from the 90s. Are those two events independent?
Yes.
No.
No, you don't know.
So are they independent? I'm asking, does the first penny have anything to do with that second penny? Will it affect the probability that the second penny is from the 90s?
No.
Huh. How is this different than the card example? Why was it important to put the card back into the population and shuffle it? Yeah.
Because there's only a set number of cards that you're grabbing from, as well as other blacks. So by taking a card out, you're disrupting the distribution of cards to the rest of the deck.
All right, so it has to do with, is there a finite number you're messing with?
Yeah.
Is there a finite number of pennies from the 90s?
Yeah.
So actually, if I remove that first penny and put it in my pocket, and I go to select a second random penny, even though the probabilities have only changed by a super tiny minute number, those events are not independent. If the first penny is from the 90s, there is now a slightly higher probability that the second penny will not be from the 90s, because one of the 90s pennies has been removed from the population. Does that make sense?
Yeah.
So even if it's a tiny thing, this could affect it. Like right here on example B, shuffle a standard deck of cards, turn over the top two cards one at a time. Define events A as the first card's a heart, event B, the second card is a heart. Are events A and B independent?
No.
No. Yeah, so we could say not independent, or we could say dependent.
What is the first card independent?
Independent of what, though?
The rest of them.
Like you can't really talk about independence until the second card is drawn, because independence is about a relationship between two events. So not independent. So we could say, knowing what the first card is, let's actually do this. Once we know the first card, suit, then the probability probability of getting a heart for the second card will slightly depend on what the first card was. If you draw a heart on the first card, the probability will go down of getting a heart the second time, because there's one less heart to choose from. If you get a non-heart, the probability will go up, because now there's less non-hearts to choose from. All right, last example with this. Sometimes it's actually tricky to determine if two events are independent or not. Like in this example, is is your handedness independent of your gender? Who thinks it's independent? A few. Who thinks it is not independent? No one. All right. Here's our events of interest. Female and right-handedness. Are female and right-handedness dependent or independent? In situations where it's hard to tell from the context, just actually check the definition. So we could check, is the probability of being female given you're right-handed, is that equal to the probability of being female? And is the probability of being right-handed, given you're female, the same as the probability of just being right-handed? If these things hold true, then they're independent. If they don't, they're dependent. So let's start with this first one. The probability of being female, given you're right-handed. So what is that probability? How many right-handeds do we have? 24 right-handed. And of those, 18 are female. So does 18 over 24 equal, the probability of being female is, there's 21 females out of 28 students. Do those equal each other? So this would be 3 out of 4, and this would all, hey, that one worked. Let's check the other one. The probability of being right-handed given you're female. So if you're female, and there's 24 females, of those, I'm sorry, there's 21 females. 21 females, of those 18 are right-handed. Does that equal the probability of being right-handed? So there are 24 right-handed people out of the 28. These both reduce to something?
6 out of 7.
Yeah, cool. So what's our conclusion? Yeah. To be independent. If they were slightly off, they would be not independent. Yeah.
Is it possible that like the criteria is met for one of the situations and not for the other?
No. 2 events are either independent or not. Oh, you mean right here?
Yeah, like is it possible that it works for female given right-handedness, but not for right-handed given female?
That would be an interesting thing to try to come up with a 2-way table that would create that condition. Is that possible? I don't know off the top of my head. Like, are you saying do both conditions need to be met or only one?
Or is it possible that one condition is met but the other one isn't?
Well, let's go back to the definition and see if we can answer that. It says this probability and this probability has to hold true. But I'm curious if you could actually come up with a situation where that wouldn't work. That'd be interesting. One of the most helpful things in conditional probability is tree diagrams. And you've probably made one of these before, maybe in Algebra 2. So like on this one, a computer company makes desktop and laptop computers at factories in 3 states: California, Texas, and New York. The California factory produces 40%, Texas 25%, and the remaining 35% are made in New York. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70 and 50% respectively are laptops. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center. We're eventually going to try to consider what's the probability that the computer is a laptop. But to answer this, we're going to create a tree diagram. So what we're selecting here are computers. And of those computers, there's 3 different options on where they could have been manufactured. 40% of them are manufactured in California, right? And what were the other percents?
25 for Texas, 35 for New York.
And let me pause there. What do you notice about these 3 numbers? Like, yeah, the sum of these 3 numbers is 1. And that's because this accounts for 100% of the places these computers could have been manufactured. Next, we have to worry about whether it's a laptop or a desktop. So for California, 75% are laptop, and that leaves 25% to be desktop. Texas was 70. That leaves 30% to be desktop. And this was 50-50. So how is this actually helpful? Well, there's 6 conditional probabilities in this problem. And we can find each of them using the tree diagram. Here's how you use the tree diagram. Say you wanted to find the probability a randomly selected computer was manufactured in, let's say, California and was a desktop. So what you do is you go California and desktop. And you multiply these 2 probabilities. So the probability of California and desktop equals the probability of California times the probability of desktop given California. This is called the general multiplication rule, and it works for independent or dependent events. So let's see what that actually is in this case. 0.4 times 0.75. Is that 0.3?
Yeah.
Okay. So this one, oh wait, that's for this top one for laptops. This would be 0.3 up here. Down here would be 0.1. So 0.3, 0.1. This one would be something else. It's like 0.175. Any questions so far?
Yeah.
Yes.
Where are you getting the 0.3 and 0.1 instead of
This and this.
Yeah.
You follow the tree diagram and multiply all the numbers you encounter. So like for this next one, right here, I'm going to do 0.35 times 0.5.
Oh.
And a good way to check to make sure you did this right is at the end, everything should add up to 1, since it accounts for every possible scenario. Yes?
In this situation, since there's just 2 for each state, can't you just, after you find the first one, just subtract it from the original? So you would subtract 0.25 and 0.175 to find
Yeah. So, well, what would you subtract it from? Like when you get this.
After you find that, you would subtract it from 0.25.
From this.
Yeah.
Good thing to note. These 2 numbers right here have to add to be this number. right? Because what this number represents is 7.5% of all the computers in this distribution center are desktops specifically from Texas. So actually, what's the most likely, if you randomly selected the computer, what's the most likely specs that computer would have? Like, where would it be from? Yeah.
It would be a laptop from California.
Yeah, absolutely. All right. So let's see what the actual question is. Find the probability that the computer is a laptop. So we need to find all the laptops. That's right here, here, and here. Add up all those probabilities. What do we get there? Cool. So good questions on the AP or on my test would be to give you a tree diagram and leave some pieces of information missing. Is it still recording or is it dead?
It's still recording.
But it's almost ready to die. All right, let's do the last example really quick. You randomly select 2 marbles from a bag containing 15 yellow, 10 red, 12 blue. What's the probability that the first marble is yellow and the second marble is not yellow? A, if you replace the first marble, and B, if you do not replace the first marble. Yeah. Well, let's see. Probability of, let's do example A first. Probability that the first marble is yellow. So probability of getting a yellow and the second marble is not yellow. Not yellow. All right, if you replace the, okay, so the general multiplication rule says this will just equal the probability of yellow times the probability of not yellow given a yellow has already been drawn. But in this example, if a yellow's already been drawn, but then you put it back